Okay, I got the suggestion to make a start. So we'll start. Thank you very much for coming. Well, first of all, thank you very much for inviting me to give this talk. And thank you very much for coming and listening. I collected a few projects from the last few years and put them together and try to put some kind of a thread connecting them. And the thread is acoustic, but nonlinear acoustic and fluid structure interaction, acoustic structure interaction. So my name is Dada Vital. I'm from Queen Mary, University of London. And I think it's always appropriate to acknowledge the people who helped and contribute to the project. And I've written them here. And if anyone I forgot, I apologize. And also the support that has come. So what we're going to talk today, I will start with supersonic Z noise. This is work that we've been done in our chamber. And we've done also some modeling. We've been looking at a component called Crackle. Then from there, I will use the thread of nonlinear acoustic to go to what has been in the news lately, and that is on fusion reactor, to see how we can use a nonlinear acoustic in order to compress plasma and get to fusion conditions. That involves some kind of structure and acoustic interaction. From there, I will move to the blade profiles, the work that we have done. It's also for renewable energy. And if we have the time, we'll talk on linear sound, thin structure interaction. This is linear acoustic, linear dynamics. So the first topic is the supersonic Z noise. And this diagram was one of my previous PhD students. And it has the three known components of supersonic Z noise. The first one is we have over here the Mach wave radiation, and that is created because we have eddies that are propagating in supersonic speed, and they are like little projectors, but with finite time span, and because it's a finite time span, they generate what someone could call weak shock wave or Mach wave radiation, and that is in the Mach direction. Now, if the Z had been ideally expanded, and that's it, we have the Mach wave radiation and then quadrupole noise, supersonic generated noise. But when it's not imperfectly expanded, meaning when the pressure at the exit is not equal to the ambient pressure, then the mechanism of nature in order to try to balance the pressure is through a diamond structure that we see over here. It can be overexpanded or underexpanded. And this shock wave, this diamond structure interacts with the shear layer, and it creates what we call broadband shock noise that propagates backwards. And at the right frequency, it will interact with the lip of the nozzle, if the lip of the nozzle is thin enough, and that will create a screech noise. So that screech noise is a very discrete noise. And this has been quite well known as in the 50s, 60s. In the last 30 years, 40 years, people have been looking also at the fourth component, which is Kraken, which I will talk in a minute. So that was, here is a nice spectrum coming from this review, quite old, from 95. And we see here the screech noise and the broad shock noise, and we have the turbulent mixing noise. And this is a diagram of our, not big, moderate size acoustic chamber that was designed for supersonic Z noise and or high subsonic. The nozzle here, the exit is about 3 inches. It's a small nozzle. It's a cold Z. It's coming from a reservoir that we have. The background of the reservoir is in room temperature. And we see over here the kind of spectra that we got, and it fits quite well with what was TAM's F and G spectra. So we got quite a good agreement, but we're getting in our microphones are set here. It's not exactly conventional way. Conventional way would be more in an arc, but this is just due to structural requirement. We made it in this way. Oops. Okay. The next part was to try to control that, and there's several ways to control, to reduce the noise. And one mechanism that we tried was to try fluidic injections, and we put it tangential. Usually the way to do that is to put normal into the Z, but put tangentials to give it extra swirl. And this is the near field SPL and the far field, near field SPL for clean Z, and with a fluidic control. And we can see there is a reduction because we reduced the mixing region. The mixing region, I'll go up, is over here. This is the mixing region here. And we can see here also a reduction. I can see my face. I don't see completely the diagram here, but we can see here the reduction. The blue line is the clean Z, and the other ones are two configurations that try for fluidic injection, and you can see the reduction. Okay, so that was a PhD about 10 years ago. However, this is not all the story, and this is what I wanted to talk more today about it, and that is Crackle. And the Crackle is random burst of noise, more or less in the Mach direction, but it's not the Mach wave itself. And it can amount to about 30% of the overall acoustic power. And the problem with Crackle, it doesn't really show up in power spectrum. We definitely can hear it. And there was a seminal paper in 1975 by Fox Williams, where he defined looking at the skewness. And he said the skewness, when we look for P in time, if it's higher than 0.3, then you could say it's Crackle. And he meant Crackle in the far field. Later, G and Sparrow also suggested to look at DP, at the time derivative as well, again, the 0.3. Now, there's been some question where Crackle is coming from. We know it's coming from the mixing region. Fox Williams claimed it came from weak shock waves. Others claim to it only hot jets, what they call its micro explosion of hot gas. What we think is that Crackle is really also has a nonlinear acoustic dominated. So the first thing that we've done was to try to model to see whether, let's say we don't have a Crackle. So Crackle has it's a random source. We have a coherent source, and we modeled it as a wave packet. And then we went to Westerfield equation, which is a weakly nonlinear equation. You can see it over here. That's the part of the weakly nonlinear. And we solved it. And we put here the wave packet here, and we try to have the wave packet form as close as possible to what you're getting, what was reported in experiment. And we saw we really, as Kraken claimed in the 80s, that we're getting strong nonlinear effect when the SPL is higher than 160 dB, which is quite high. So then we went and we look at the skewness, and we see that although the source is not random, that was quite old, the 2013, we do get skewness that can look like Crackle. And this is quite of a distance from the source itself. So that gave us a question whether nonlinear acoustic can disguise Crackle noise as, can disguise noise as Crackle. So from there, we went into the lab and we did some experiment. And the experiments were on MZ, that's the Mach number for equal to 2. The design had been ideally expanded at 2. And we looked at two components. We looked at discretes. So that was in the sideway, the harmonic. And then we also looked at around the Mach direction. And to our surprise, although it was a cold jet, when we recorded that, using our ears and listening to it, we heard Crackle. And that we were quite surprised because until then, all the experiments that we heard, we saw that Crackle was from hot jets. So we did some analysis on the time history. And this is what we think the Crackle here is happening. It's not a very strong Crackle, but we do have steepening here. And this is in the far field, not in the near field. So we decompose the two signals. So we have discretes that is in the sideway. and the crackle is around the 40 degrees around here. And it is in the far field. So that gave us the understanding that the crackle can happen also in cold jet. So it's not necessarily due to micro explosion of hot air, gas, or so on. Some people complain that can also cause crackle. We didn't say it doesn't, but we say that crackle can also happen in other conditions. We went in order to categorize that, and we noticed the crackle only in underexpanded Z. We didn't notice that in overexpanded, because in underexpanded Z. So we wanted to go and to see the nozzle, the effect on the nozzle pressure ratio, on the skewness in the pressure, and the skewness in the time derivative of the pressure. So you have here the nozzle pressure ratio, and that's the color. So most of them, as you see, the crackle is standing here around the 30 degrees, 35 degrees. That is where we see high skewness. When we looked at the screeds does show high skewness around the 90 degrees in P, but it doesn't show in the PDT. So we believe the PDT is still, as sorry about there's a train passing through. We believe that the screeds in the PDT is important in order to identify crackle. So that was one of the conclusions from our work. I would like to continue that work, but what I would like at the moment is to jump to another topic, and that topic is for renewable, and to see how nonlinear acoustic goes into the design of magnetized fusion target reactors. I'm not sure how it goes with a question, whether the question given online or talking. We have Zoe on the background, so she probably knows better than me. So I will go to the next one, and this is quite next topic, and that is electricity and renewables, which is a topic that we all hear in the news and we all know about that. And this is a projection that was actually made in 2017, it's still holds now. What will be the need for new energy resources? So the biggest one, it's come from the International Energy Agency. The biggest producer, and by miles the biggest producer, is going to be China. And we see quite also big increase in India. In the European area where we are, there will be some increase, but it will be moderate increase. So the biggest increase is here in China. United States will have some increase, but those countries that are fast developing is where we see the big increase. Japan and Korea will show a small increase in energy production, in electricity production. This is where hydrogen fusion comes. It's running after hydrogen fusion. I thought putting this slide just quickly, this is not acoustic, just quickly to talk about what we do hydrogen, is that we take isotopes of hydrogen, we take out the electrons around the nucleus to help it to fuse better. And then we have high speeds, and these items, either we compress them like on the sun, where we use gravity to compress, or we accelerate them. So they hit each other, they collide and fuse. When they fuse, we will have a generation of energy, and that comes, and also we have new particles, and that comes in helium and neutron. And what we would like is to do it in a safe way, and to be able to capture this energy, and to do it in an efficient way. I mean, we know how to do it in the 50s. In the 50s, we did that for bad things, destroy other people. So what we want to do it now is to do it to generate energy for humanity. One good outcome also from fusion is, compared to fission, is that fusion reactors have less radioactivity, much less than that. They still have that, we still have to be careful, but the radioactive component is much smaller. The two big designs The first one is the Tokamak, which requires a lot of money, talking about billions here. So there's a relatively small tokamak here in the UK, the Z facility, but the big one is North South France. We're talking about billions, and the idea is that it's like a donut, and you accelerate isotopes until very fast speed until they start colliding and fusing. On the other side, where we have the inertial confinement, this is where you want to compress, and this is what comes from NRF. That's quite a large hole, and you're using lasers, and this is the target. Okay, so the target of all that thing is smaller than the size of human eye. So both these things require considerable amount of investment, and obviously it has to be government investment, leading by government investment. There is a middle way, third way, and that is the magnetized target fusion. This is what I wanted to talk today. And this is where nonlinear acoustic comes. And we've been working with a company, General Fusion. They're based in Canada, near Vancouver. And they are trying to take into what they say, the advantage for both sides, to take the magnetic confinement from here. So still going to use the magnetic confinement, the plasma. The plasma is the gas where it contains the isotope of the hydrogen that we want to compress, and also to compress using a mechanical compressor, in this case, acoustic compressor. So what I would like to do now is to stop the sharing and then to put one of their animations. Before I put that animation, just want to say that I do not promote a certain company. I'm not employee for a certain company and so on. So there is a bit of a commercial thing here. So please don't look so much at the commercial thing. Just, I think it will explain better than what I can do flapping the hands and using the speakers at the moment. So it will take just a second. I will stop sharing. And I will go sharing again to this one. And I will start running it. Okay, so I'll stop sharing this one. I'll go back to share our original slides. So it was more like a promotion, but I think people understood what happened there. We have pistons here. They are gas pistons, steam pistons. They generate a pulse. They hit. So the hammer goes down. It hits an anvil. The anvil generates an acoustic pulse that goes and will try to compress what we have over here. It will compress. So this is the liner. It will compress the liner, and that liner will compress the plasma. That is the idea. So you have a piston, a hammer hitting an anvil. The anvil is steel. The steel is moving the acoustic pulse into the liner, which is melted liquid metal that it keeps rotating, and that generates a pulse. As well, at the end it will be a shock wave, but it needs to generate an acoustic pulse that goes pressure wave. It goes inside, it compresses the liner until it gets into the gas, the plasma gas, and then it will compress the plasma gas. That is the idea. So this is where the nonlinear acoustic comes. They build, this is demonstrator. It's not just a demonstrator of the technology. This is not a prototype. And these are, there was supposed to be more. There are only 14 pistons here. There are supposed to be about 200 pistons in the design. And that is the reactor. So the whole reactor that is for the demonstrator is, the diameter is about 1 meter. This is what we are talking here. What we wanted to know is to analyze it, to see what happened. What is the efficiency? How the sound propagates from the hammer to the anvil, from the anvil to the liner. What does the liner do? Will the liner be able to compress the plasma or not? And will it be able to do it in a fast way? So for that, I just put it there. This is a typical diagram of power station. So the only difference is that you have over here the reactor, which is a reactor that's a fusion reactor, but it could have been something else. And we have the heat exchange, the condenser, and we have the familiar cooling generator. So our attention is over here, not that part. That part is conventional part. So our attention is on the reactor itself. So we published that in 2017, and we simplified the debate. So initially we said, let's look at a single piston model, and then we will look at a multiple piston model. We gave them our code, which I'll talk in a minute. Our code is a fluid structure interaction. And they also used OpenFOAM. They used OpenFOAM for inside. We used the Westerfield solver for the inside. We gave them our code, and they used the structure code, which is based on, here it is. It is based on putting finite element with discrete element together, combining them together, and then you're getting Glatz deformation. You can also look at fracture, and you can look at fluid coupling. I think I can give that a 1 hour conversation on that, on the numerics of that. This was led by my colleague, Anthony Zouza. I'll keep it probably for another time. So just giving you an example of what the code can do. That is impact for plate. And we have here the spread of the shock coming from the impact of the plate. And we are getting the cracks occurring. And it quite fitted. I didn't put it here, but it quite fitted the experiment. So it worked okay. It was accurate. So back to our problem. So our problem, we went over here and we did the first hitting here by the piston on, so it's the hammer hitting the anvil. And this is what we see over here. The hammer comes here and we have the anvil, and look at the times. We are looking at very, very short times. We're looking at micros of second. And the reason for that, it's because plasma has a very short time, a lifespan. So we have to do all the compression and to get fusion condition in a very short lifetime, much less than a second, of course. So we have here hitting the hammer, hitting the anvil, and we're getting the acoustic pulse getting inside, but there is also something coming back. And that something coming back can cause a problem, because we'll see a bit later, we will have ear cavitation, particularly if we have quite large pressure waves leaving the anvil. And that cavitation, these bubbles can blow, and then can cause face, so it can cause damage to the face of the anvil from the side of the liner I'm talking. We took this one as an initial condition, and then they ran OpenFOAM. We ran the Westerfield, that equation that I put at the beginning. If we use it for the wave packet, same equation that you solved just for the pressure, that is weakly nonlinear, and the OpenFOAM was solved full fluid dynamics. Remember, this is liquid, this is not gas. So also the equation of state can be important. And we got quite a good agreement, as you can see. So we're looking at 100 microns, 150 microns, 200 microns, and we got what we wanted here. We're getting good compression. The problem starts here, is that we are getting what happens behind the front of the wave, is we're getting very low pressure, and this is where the cavitation, the Westerfield, of course, couldn't get it. So the fitting between the Westerfield around the piston and what open foam said did not work that well. But the front worked pretty well. If we can look here at these lines, these are the lines of the path. So if we're looking at going, sorry about that, we're going along the path from here to the inside. So we actually have all these pistons, and we're going to the inside. So one way we're going from the center of the anvil to the center of the reactor, and the other path is we're going from the middle to the center of the sphere of this reactor. So this line is the line from the center of the anvil. Center of the anvil is over here, and the center of the reactor is here. And we see we progress in time, and we see quite a good agreement between the different solvers, but what is happening is here, that's not a good agreement. This is where we're getting the cavitation. If we go over here, that is between the anvils, and between the anvils, we're going towards the center of the reactor. This is quite a low speed damage speed. That's actually 150. So this is a low speed. Again, we're getting good agreement. And because we don't have so much problem cavitation, we have a bit of problem here, but we have a good increase in the pressure. Here we started about 0.3 gigapascal, and we are just towards the end, we are just at 0.4. So what happens here is instead of increasing the amplitude, the wave more spreads azimuthally and increase the amplitude in the polar direction. This is okay because we want uniform compression. If we increase it to 50 meters per second, then that again, this is from the center of the anvil to the center of the reactor. And now we start to see the difference between if we use a linear equation of state or non-linear equation of state. This is the Tate equation of state for liquid. And that shows to you that particularly for this one, we have to be careful what kind of equation of state we're using. On the line that goes between the anvil to the center, the agreement is much better. Okay. Now that design was one of the designs that was pursued. I picked up that it's not the winning design. I picked up this design because it involved acoustics. There are other designs that are more, I would call them aerodynamics or hydrodynamics, and in the summary I will give references to them. So this design at the moment is not continuing, but some of the lessons that were taken from this design went to the new designs. From here, I would like to go to the third topic, and the third topic is again on renewables, but now it's not fusion. We're looking at kinetic turbines or wind turbines or can be marine turbines. And this is a method that has been developing, particularly developing with my colleague Theo Alexander in the last, I don't know, 7-8 years. He actually started with it, and that we call the circle method. And that method is where we argued, sometimes against resistance at the beginning, that in order to design the blade correctly, the profile correctly, we have to look at the third derivative of y. Y is in this direction. So we have to look at the curvature and derivative of the curvature of the blade, and particularly we have to see what's going on here at the edge. And we got some resistance because most people know the first order of thin-fold theory, where y, the third derivative of y doesn't mean anything. But I think we have done CFD, we've done experimenting to solve that. First, I will start with a bit of the aerodynamics. Excuse me, I know this is acoustic, but they are connected. So the early design was for compressible, it was runs, ANSYS, and we actually got YL and ZL, these two. C2 are the new designs, and we are getting that we get less losses. So the question was, what is happening? So we went back to the drawing board, as you say, and we decided to look at the low Reynolds number applications, small kinetic wind turbines. We pick up the Eplos 387, which is a common one for this kind of, it's asymmetric. And we designed it using our method, we named it A7. And as you can see, the differences are not that big. This is actually expanded in the y direction. Yes, it's quite thin. So it was over here zoomed. Otherwise, we wouldn't be able to see the differences. But these differences are still important. We also used our own code. So this is the Y code that General Fusion used, but we put it together with our own flow solver. We call CGLSY, and it is based on CGLS is based on finite volume, quite standard LES there. Okay, so this is a bit just to convince everybody that what we're doing was okay. So this is a CP contribution, CP that is coefficient of power, and so it consists of pressure, and we took the minus part of it, so that is the upper surface, and this is the lower surface, and we got quite a good agreement with an experiment that we've done on our wind tunnel. And this is again doing our experiment. This is not acoustics. I'm going quickly through that. The main thing was that we got a reduction in CD. What we were interested in is in terms of why it happens. Why do we get this reduction in CD? We got that because we delayed stall. One of the reasons delayed stall is that we managed to keep there are two separation bubbles. One is a little one, which I'm pointing right now at the leading edge. There is another one over a bigger one, laminar separation bubble. When this little one blows up, we get full stall. And because of our modification, we managed to keep it for a longer time for higher angle of attack. So it blew up later. And that was the reason for getting low drag, and we delayed the stall. Okay, so this is the aerodynamics. And we can see over here the effect. This is actually for NACA 0012. Same thing, same exercise done. The bubble still exists. This is aerodynamics. Then we go to the question, that affects stall. Will it affect also noises and generations? Obviously, we will not get stall noise because we're delaying stall. But what happens at low angle of attack? Now, this is low Reynolds number. That low Reynolds number is dominated by tonal noise. We have laminar boundary layer. I'll talk about that in a minute. We did not have the facility to do the experiment. We did have a project funded by the Royal Society, NSF, so that was Behang. So we used their facility, and we sent our models over there. So we produced the models, we sent it over there, and we sent also a student, and the models were tested there, and then they came back, and we analyzed that, and we were surprised by the very good results, which I will show in a minute. So first of all, so this is the condition that we were looking. This is, we have the laminar boundary layer. The airfoil is dominated by laminar boundary layer, and we have vortex settings. So this is the condition that we are interested in. This is lower the Reynolds number than 400K when based on the code length. We also tried that, and here, when it's dominated by turbulent boundary layer, we found that our modification doesn't do a lot of change. So our modification was important here, not that important here in terms of noise generation. So this is the results, and that is the results that we have. I think that was done for 400K. There was quite a lot of background noise, so we had to deduct that. So this is A7, our new design, and that is the Eplos 387. So we took the Eplos 7, we designed using A7, and we put it into the acoustic chamber that they have in the wind tunnel, and we can see the effect. And that is the effect at 5C on the sideway, and that is 10C. So I think we were quite surprised that we got quite a good reduction of here, I don't know, 7 dB, and here it's about a few dBs. And that's a very, very small difference in the airflow. We put that also at several Reynolds number. As you can see, as the Reynolds number increases, generally the difference is small. We don't have any difference in terms of what's called the broadband noise. The difference is in the peaks. This is what happens. That's in the tonal noise. It was published in 2017. And we did afterwards, we did some large eddy simulation to see what is happening. So on the left side on the screen, we have the EPLA. On the right side, we have the new profile. And what we noticed is because of our modification, we managed to move the big laminar separation bubble, the one that is after the maximum thickness, a bit upstream. And because it moved a bit upstream, the interaction between the flapping of that laminar separation bubble and the trailing edge, which is somewhere over here where I point, became smaller. And that interaction reduced the noise. This is what we believe. Reduced the noise. We also used a bit our LES, but our LES was based on curly, that light hill curly analogy. And we noticed that it's a similar, we get a similar qualitative reduction in the noise. Take into account that the LES does not have the background noise. We also have the background noise. So this is where we stopped in the laminar separation bubble in our method. We are now trying to implement other methods as micro vortex generators and morphing, which probably is for another time. I think we have another 5-10 minutes we can talk. So I will talk on, I prepared quite a lot of slides. I'll go through that. That is the fourth topic. And this is more analytical topic. It started 2011. And this is where we looked at the interaction between thin cells, structures, fundamental structures, like this one is a cylinder. And we have a sound wave coming and see what happens, how the cylinder happens, and want to put some complexity. For example, if we have a free surface, a zero pressure surface, as I said, it's quite analytical. We have expansions. We use a Fourier expansion, whether it's a Bessel Fourier Bessel expansion, Fourier Alexander, and so on. And you try to match after that. You match the coefficient. You find the coefficient. It can be in spectral space, or it can be in the real space, the collocation. What I wanted is that if you look at that, you could see that actually, in practice, it's very difficult, of course. A computer can do that. If you have a certain deflection of the cell, then it will make the cylinder acoustically cloaked. That means there will be no backscatter, no scattering of noise coming back. Theoretically, it can be achieved using infinite number of pressure actuators, but in reality, it's not practical. But it was interesting for us to see whether how many actuators you need to get in order to get a reasonable reduction in the noise. So this is just a general way we have the noise generation, and we also had some waves inside the cells. We could put some water inside as well. The outside was water, so the noise coming was from here, and what we see is the externally scattered noise. Then we ask ourselves how we can cancel that. So we just calculate what would be the deflection, and this is deflection. So it's quite complicated. So the higher the frequency, it becomes more and more complicated. So for low frequency, you can try to do something. For high frequency, it becomes more complicated. So we just put 24, for example, line surface pressure actuator, and you could get some reduction in, as you could see, if you compare the two fields. So we continue with that. For example, we looked at sphere. So in a sphere, we said what will be, we put 7 actuator, and you can see for low frequency, the sphere radius is 1 meter. So we could see that we can get quite a good reduction in the far field. The penalty that you pay is the near field. The near field becomes higher. And that is something like what is called the target strength. And you could see that for low frequency, you could get very good reductions, but when you get to high frequency, the difference is becoming quite small. So this is very theoretical. The other point that we tried to look was another example. We looked at the free surface. We asked ourselves what will happen when you have a plate on the free surface. So the free surface is over here, and the free surface is hinged. Can we put just a uniform external force to reduce the scattering? We actually derived a very simple formula for that, and the answer is yes. It works quite well, but for low frequencies. When the plate is not highly non-compact, I would call it. When the plate is compact or close to the limit of being compact, it can work. But when the plate is highly non-compact, it doesn't work, and it's obvious that uniform force will not work. The last thing that I wanted to talk is on Janus. There's been quite a lot of people talking about Janus. The Janus sphere type, it's that you have the sphere is based on two different surfaces. You can have hard and you can have soft. And that has been looked a lot for chemical. It can look for a lot what we're looking at now, not going to acoustic, is for micro swimmers, that you can heat them, and you can use the heat, the asymmetry to use the thermal, different thermal behavior to start moving them, or you can use an external electric field to move them. What we wanted to look here is in terms of the acoustics, and in terms of the acoustic, we wanted to look at it is in terms of the reflection. So we have here a free surface, and we have a hard sphere, and then says, okay, let's put here the soft sphere, and then we have the hard sphere. Will it reduce the reflection? Yes, it did. It did reduce the scattering, not completely, but you can see it did. And the penalty that you're paying is that you're getting a bit more between the free surface and the hard surface around here. But again, this works well for low frequencies. When you start getting to higher and higher frequencies, the reduction in the scattering becomes smaller and smaller. So it works well for small objects, I would call it, as compared to the incoming wavelength. We also looked at, I think this is the last one, we looked at a case where we have a sphere filled with oil, and we said, let's see if we could put like a little speaker. This is all theoretical inside, and the same thing can happen again. You can get a zero reflection, zero scattering if you want, but then you have to put higher and higher. So it's not just a monopole dipole, you have to put higher and higher expense inside of the center. And that's what was to try to tell you what is the higher mode number of cancers scattered the sound, and what is the frequency, and how much a reduction in scattering noise you get. That is the idea. It's a bit difficult to try to read this contour plot. This is what more or less I wanted to talk about. So I will just summarize. There's been quite a lot of topic. I went flying through them. So the first thing I talked was on supersonic jet noise, and we looked at the wave packet, and we just, again, we verified what Kraken said in 1986 when we're getting the SPL inside an 160 dB. It's really highly non-linear, but the other thing that we found is that the crackle can appear even from a random, not a random, non-random source to look like crackle. The sound can look like crackle. Difference between crackle and screech, and that we found experimentally, is that in crackle that we have high skewness both in P, in the pressure, and in the PDT, while screech has just high skewness in the pressure, not in the time derivative. And we found experimentally evidence of crackle in lab small cold Z. We looked at nonlinear acoustic for the design of target fusion reactors. Mostly there was good agreement between the nonlinear acoustic model and the full CFD. The hammer, when you have high hammer, high speed, when you really need to good modeling of the liquid equation of state. there was a problem there of cavitation that is not accounted by nonlinear acoustic models, and other designs, I have to say, are possible. Some of them are in these references. So the designs are moving forward. This is a really fast-moving field all the time. The blade acoustic, we looked at the method that we designed. The idea of the method is that you will have to have smooth in the curvature. We claim that you can relate it to the second order of the phi-full theory. And what we found that it delays toll, but in terms of acoustic, we found that it can reduce the tonal noise, and that was by reducing the size of the laminar separation bubble. And those reduced the laminar separation flapping, the interaction between the laminar separation bubble and the trailing edge. And last thing, I just showed some mathematical expressions of what we did of linear interaction between fluid, sound, and cells, and so on. This is what I wanted to talk today. And thank you very much for coming. And I think that I'm more well in time. And if there are any questions, there is one chat there, but I'm not sure what it is. Yes, so I am fine. I'm fine with that at 2 o'clock. So they stop sharing. I can stop sharing. And if there are any questions, I'm happy to answer. Thank you, Samuel. Okay. You're welcome to contact me. I didn't write my email. I can write my email if someone wants more information. So my email is, and you're very welcome to contact me if you have any questions, or can everybody else can see that, to host and panelist. I think to everyone, I need to write it again. So this is my email. So you're very welcome to contact me when, and I'm very happy to talk with you. Anyone wants to collaborate or has question, please email. Okay, I think there are no questions. So thank you very much. I'll stop sharing. Well, thank you, Christian. And I think Zoe can go online again. Oh.
Hi, Eldad. Thank you very much for that. That was great. That we very much appreciate you coming on board and presenting that. There's been a lot of interest there. Thank you very much for your time.
Thank you. Thank you for inviting me.
You're welcome.
Okay. All right. Thank you.
Thank you.
Bye.
Bye-bye.